Generative AI can write complex code and create incredible art in absolute seconds. But have you noticed that when it comes to physical robots, they seem totally out of their depth? Welcome to today's Explainer. We're going to dive right into the core paradox of modern AI and look at how a massive breakthrough, something called spatial intelligence, is about to completely bridge this gap. Think about it. If you've ever watched a video of a state-of-the-art robot doing something totally basic, like, I don't know, folding a shirt or picking up an apple, you probably noticed a tiny disclaimer hiding in the corner of the screen. Almost every single one of those videos has to be sped up, sometimes by like 8 to 10 times their actual speed, just to look normal to us. So it begs the question, why is AI so incredibly smart in the digital realm, but robots are just so remarkably slow in the physical one? Well, the root of the problem is a massive data bottleneck. Think about large language models for a second. They basically have the entire internet at their fingertips, billions of pages of abundant text and human knowledge to learn from. But robotics, physical data is severely scarce. You can't just download the physical laws of a messy, cluttered kitchen from the web, right? A robot actually has to move atoms through physical space. It has to deal with gravity, friction, unexpected obstacles. This severe lack of real-world training data is literally the wall the robotics industry keeps crashing into. So here's our roadmap for today. First, we'll look at the robotics data bottleneck. Second, defining spatial intelligence. Third, the real-to-sim pipeline. Fourth, why simulation beats reality. And finally, number 5, the pragmatic robotic future. All right, let's jump right into part 1, the robotics data bottleneck. Right now, one of the main ways researchers actually teach robots is through teleoperation. This basically means a human wears a specialized rig or uses controls to puppet the robot and show it how to do a task. But, this method is fundamentally flawed if you want to scale up. When you rely on teleoperation, you're collecting data at a speed that is actually slower than a human doing the task natively. And not only is it slow, it's incredibly costly, and honestly, in some environments, it's flat out dangerous. You're hard-capped by human physical limits and the laws of physics. So if we want those mind-blowing exponential scaling laws we saw in language models to apply to robotics, this manual data collection simply isn't going to cut it. Moving right along to part 2, defining spatial intelligence. This concept right here, it shifts our entire paradigm of AI. We are finally moving beyond flat text and 2D images. Spatial intelligence is defined as creating AI that has the ability to generate, understand, reason with, and interact with physical or virtual spaces. Basically, this means building large world models that are geometrically consistent across space, time, and different viewpoints. So if a robot pushes a virtual object forward, it shouldn't just magically disappear, like it might in a glitchy video generation model. It actually needs to obey the structural, hard logic of a 3D world. To really grasp why these 3D world models are so absolutely vital, AI pioneer Fei-Fei Li points out that human intelligence relies heavily on internal simulation. I mean, think about it. When a pro soccer team is prepping for a World Cup game, they're at the whiteboard, visualizing plays, and running simulations in their heads. They're anticipating, okay, what happens if an opponent moves left instead of right? They are literally training for the game before their cleats ever touch the grass. Robots need this exact same ability. And the crucial mechanism making this possible is called counterfactual reasoning. This is playing out events that haven't happened, or maybe cannot happen, or honestly, situations where you just don't have enough real-world data to make them happen. While you play it out in your head, or in this case, a digital simulation, you learn how to act. Because, let's face it, we can't possibly collect enough real-world teleoperation data for every single crazy edge case a robot might face. The robot absolutely must use counterfactual reasoning inside a simulated digital world to safely figure out how to react. Which brings us to part 3, the real-to-sim pipeline. So there's this company called Scenix, and they're developing what they call a real-to-sim-to-real pipeline to build a continuous learning loop. Step 1 is mapping the real environment into the digital world, and they're capturing not just how things look, but the exact geometry and physical dynamics, like how objects actually react when you apply force to them. Then, step 2 happens entirely inside this massively scalable digital twin. Here, the robot can generate data, evaluate its own performance, and train at a huge scale. Finally, step 3 is taking that highly trained, super intelligent policy, basically the robot's newly trained brain, and deploying it seamlessly back into the physical robot out in the real world. Now, here's a really important distinction we need to make. This real-to-sim pipeline, it isn't about physically building a robot body. You won't see them 3D printing metal arms. Instead, they're building a flexible model and embodiment-agnostic infrastructure. So whether someone is using a single robotic arm, a bipedal robot, or a mobile warehouse manipulator, this software platform acts as the ultimate digital training ground. It's kind of like the Matrix, right? A place where any robotic brain can be dropped in to learn and navigate. All right, part 4, why simulation beats reality. The real superiority of this matrix approach comes down to reliability through systematic coverage. If you want a robot to actually be robust in the real, messy world, you can't just cross your fingers and hope it encounters every possible problem during manual testing. But in simulation, you have absolute control. You can systematically randomize the lighting, change the friction of a floor, alter object geometries, and tweak physical parameters millions of times over. This endless variation ensures that when the physical environment suddenly changes on a random Tuesday afternoon, the robot won't just freeze up and fail. Why? Because it's already seen 1,000 variations of that exact same problem. And then, of course, there's the sheer efficiency of it all. Evaluating how well a robotic policy works in the real world is agonizingly slow. You make a tweak, you run the physical robot, and you just sit there and wait. But in simulation, you can run these evaluations multiple orders of magnitude faster. Because gravity isn't holding you back in the digital realm, you can systematically speed up the robot's behaviors and evaluate its success rate, like figuring out if it works 95% of the time versus 99% of the time, in just a fraction of the actual clock time. Finally, let's wrap things up with part 5, the pragmatic robotic future. Let's take a look at the pragmatic roadmap for deploying all of this. Historically, automation always starts in structured environments, like car manufacturing factories, right? Places where you have complete, absolute control over every single variable. The immediate revolution we're stepping into right now is semi-structured environments. Think of an Amazon warehouse. You have partial control to make tasks easier, but there's still a bit of unpredictability. But what about the unstructured environment? Well, a home with 3 dogs, 5-year-old kid, and a floor completely covered in toys, that has zero control. That is the ultimate grand challenge, and practically speaking, it's just not the immediate target today. We're going to tackle the semi-structured world first. And, it's really vital to keep our own biology in perspective here. Human evolution optimized our bodies perfectly for those unstructured, chaotic environments. We have generalized bodies that can adapt to almost anything, and our brains, they operate at an astonishingly efficient 30 watts. Current AI hardware requires massive power demands just to mimic a tiny fraction of that in very narrow tasks. So achieving true generalized human-level AI, robots operating with our level of crazy efficiency, is still a very long way off. We are pretty far from having humanoid butlers doing our dishes on battery power. But hey, that doesn't lessen the incredible leap forward that spatial intelligence represents. By bringing real-world physics into digital simulations, we are finally giving AI the training ground it needs to catch up to its intellectual growth. So I want to leave you with this final thought to ponder. When this real-to-sim pipeline fully scales and that data bottleneck completely shatters, what exactly happens to our world when the physical capabilities of AI finally match their breathtaking intellectual ones? It's wild to think about. Thanks so much for tuning in to today's Explainer. Make sure you keep your eyes peeled because this spatial intelligence revolution is just starting to step out of the matrix and into our physical world.